Okay, good morning, everybody. It is 8 o'clock in West Coast time, and welcome to VSPG today. We have a presentation by Nick Tosca from the University of Cambridge. He's presenting on the kinetic controls on the early Neoproterozoic carbonate factory. Next week's talk, I haven't adjusted the schedule yet, but right now it's been postponed. Dave Evans from Yale had an idea he wanted to present on, but we're going to postpone that to after the new year, so that just for his publishing, he's working on publishing this material first. So we're going to see what we can do about getting someone in short notice, but if this isn't going to work, I'll confirm that next week. And it might work out fine because people may be on their way to Denver for GSA, at least people in the States. So more info on that next week to confirm. But for now, I don't have any more announcements. Andre, would you like to introduce Nick for us?
Yeah, thanks. So we tried to contact one potential speaker, but if anyone feel ready to step on a short notice, feel free to contact me. Alex will be traveling next week to GSA. So with this, it's a pleasure to introduce Nick Tosca. Nick did his undergraduate degree and master and PhD in New York State. For master and PhD, he worked with Stuart McLennan, and his interest, he has broad interest, but it's focused on interface between mineralogy and specifically clay mineralogy and geochemistry. So after his PhD, he spent time in Harvard University as an Origins postdoctoral fellow, working with Andy Knoll. And after it, he decided, I guess he had enough of North America and moved to UK, starting with lecturer position, starting as a research fellow in the University of Cambridge, and when lecturer at University of St. Andrews, moved to associate professor in sedimentary geology in the University of Oxford, and eventually he is now a professor of mineralogy and petrology at the University of Cambridge. So it's a pleasure to introduce Nick. As I said, his interest on interface of mineralogy and geochemistry, and with implication for precursor minerals and iron formations, but also he worked a lot on Neoproterozoic, and I guess his talk today is expansion on his interest in Neoproterozoic. So with this, I pass it to Nick.
Okay, thanks, Andre and Alex. Thanks very much for the invitation to talk about some work we've been doing on how early Neoproterozoic carbonates are formed. I'll say before I get into it that I'm going to show some data and a lot of concepts that were developed through some hard work from my graduate students and collaborators. So I'll discuss them specifically in the end, but I'll just say that this has been a huge team effort. Okay, yeah, so probably don't have to convince this crowd that the Neoproterozoic occupies a really special place in Earth history. It sort of sits right at a critical moment in biological evolution, at least taking the long-term view, and it really encapsulates a turbulent interval that witnessed the breakup of a supercontinent, some pretty wild climatic fluctuations, near global scale glaciations. And amongst that, the sedimentary record records some pretty fantastic signals of ocean atmosphere climate change. So zooming in on this time period in a little bit more detail, the whole of the Neoproterozoic encompasses an enormous swath of time. But this figure has a lot of data, which I think will be familiar to this audience, but we'll just step through it piece by piece just to walk away with some of the most important points. So what we do know about the Neoproterozoic from biomarker data is that, at least compared to the beginning of the Neoproterozoic and then at the end, there appears to be a significant shift in the identity of primary producers from bacteria to dominantly eukaryotes. And along with that, in the intervening time, a number of key eukaryotes end up appearing in the scene, as suggested by the fossil record in these red lines. But along with that, there are a number of interesting and important recalcitrant and biomineralized taxa. Importantly, which I'll talk about a little bit later, evidence for the earliest recorded eukaryotic biomineralization in the form of calcium phosphate. And then vase-shaped microfossils, which appear to be composed of organic carbon, but also are associated with phosphatic elements as well. And then in the bottom panel, we have what I'm sure is the familiar isotopic composition of carbonate carbon. And of course, as we know, the Neoproterozoic encompasses some pretty wild fluctuations, in addition to really rich background signals that appear to sort of climb as we approach the Sturdian glaciation. So a lot of what is discussed in terms of the Neoproterozoic relates to the major ins and outs of the long-term carbon cycle, of which I've summarized here. And we know that the carbon cycle includes important inputs and outputs of the atmosphere, biosphere, ocean system. And a lot of times when we talk about interpreting the carbon isotope record of carbonates, we do so in the context of some of the major sinks in the long-term carbon cycle, including carbonate burial and organic carbon burial. And a lot of the discussion on carbon isotope fluctuations and potentially climatic fluctuations have centered on organic carbon burial, but we became interested in this red arrow, really the carbonate sink. And we became interested in this from a very basic question, which is how were carbonate rocks made before calcium carbonate skeletons really became important in the Neoproterozoic? And if we can understand something about the dynamics of calcium carbonate precipitation, at least in the Neoproterozoic, how might this impacted the long-term carbon cycle? And I'll explore what I mean by those questions in the forthcoming slides. But first, a comparison between the modern calcium carbonate cycle and at least the way we think the Precambrian calcium carbonate cycle behaved, at least before skeletons became a dominant force. In the modern ocean, calcium carbonate is buried in shallow water and in deep water settings. And as we know, because of pressure and temperature constraints on the solubility of calcium carbonate, there is a horizon called the lysocline below which calcium carbonate will start to dissolve and be recycled and replenished in the deeper ocean. And that's largely driven by the activity of pelagic calcifiers, which have been a feature of the Earth system since the Mesozoic. And what's really important about the pelagic calcifiers in this deep sea calcium carbonate sink is that if there were a perturbation to the shallow water calcium carbonate sink, say, for example, sea level fall, as I have illustrated in this slide, what that would mean is that in shallow water settings, less calcium carbonate would be buried. That would cause an increase in the carbonate ion concentration of the ocean, and therefore a deepening of the lysocline. And accordingly, more calcium carbonate would be buried in deeper ocean settings. And in that way, the pelagic calcifiers or the deep sea calcium carbonate sink acts as a stabilizing force in the calcium carbonate cycle. And models that take those feedbacks into account hypothesize that, in general terms, the calcium carbonate cycle has been relatively constant over much of the Cenozoic and perhaps even longer than that. But of course, this is a major difference compared to the Proterozoic and much of the Precambrian because there's no strong evidence that there was a significant deep water calcium carbonate sink. And what this suggests is that the behavior of the calcium carbonate cycle and potentially climate is strongly linked to the dynamics of shallow water calcium carbonate burial. Okay, both controlled by external factors like sea level, relative sea level rise and fall, but then also the inherent kinetics of how calcium carbonate is formed and buried in shallow water settings. And that's really where our point of interest in this problem comes from. we kind of leave that as a big question mark because we really don't know much about how this shallow water sink behaved over time. What we do know, though, through decades of work by Precambrian geologists, is that Precambrian carbonates record exquisite detail and long-term changes in the style of nucleation and crystal growth. And I know that the Bergman group has really updated this in the last couple of years and put a lot of data behind these general relationships. But I didn't have the heart to remove John Grotzinger's original figure because it was this figure that really got me interested in Precambrian carbonates in the first place, is that I took a look at this figure and read that chapter in the Precambrian carbonates volume and was just gobsmacked by the exquisite detail recorded by Precambrian carbonates, but also, from an aqueous geochemist point of view, I was convinced that carbonates are definitely saying something about, calcium carbonate chemistry. If we could only unravel the styles of nucleation and crystal growth, we might be able to say something about the carbonate chemistry of the oceans. Now, I've added an interesting feature here onto this diagram, which includes orthogenic magnesium silicates, which appear to be present in some carbonate successions in the early Neoproterozoic. And this is where our interest in this really kicked off. And it was when I started working with Justin Strauss towards the end of his PhD that I became pretty interested in this. So we'll talk a little bit about this. And Justin and I focused on two different successions that exhibit magnesium silicate precipitation and really recorded in a variety of different sedimentary textures. But both of those successions are Tonian in age. There's the Callison Lake Formation on the left-hand side, and the Svanberg Fiolette Formation is part of the academic Rebreen group on the right-hand side. Now, the Callison Lake records subtidal to supertidal marine deposition in a largely extensional basin. It does show a pretty strong sedimentary evidence for episodic restriction in the form of things like evaporite pseudomorphs and the style of carbonate precipitation and so on. Whereas the Svanberg Fiolette Formation records similar environments, but on the whole, it's dominantly subtidal to paratidal marine deposition in what's been interpreted as a shallow shelf to lagoon setting. And most of the succession, as far as we can tell, is dominantly marine. And so there aren't any obvious geochemical or paleontological or sedimentological expressions of restriction in through this succession. But that really summarizes the major differences between these successions. Now, as I mentioned, both of these successions are associated with magnesium silicates, and this figure just shows the expression of those magnesium silicates in the carbonates at a variety of different scales. So there's an XRD trace on the upper left-hand side to sort of give a sense for what the dominant mineralogy is. So of course now it's talc. But you can see at the outcrop scale, the magnesium silicates really encompass a significant interval of stratigraphy. And at the sedimentological scale, they occur as a variety of labile sedimentary components that get reworked to carbonate accumulating environments. And then, of course, in the Svanberg Fiolette Formation, there's an interesting association with a carbonate fabric that I'm sure many of us are familiar with, and that's calcium carbonate microspar. And you can see, especially in the bottom right-hand image here, you can see this oil and water texture that's displayed by this magnesium silicate nodule within calcium carbonate microspar. And our interpretation of that is that those two minerals precipitated at the same time, and that as the magnesium silicate transforms to talc, which is hydrophobic, it actually repels itself against the mix, which is dominated by calcium carbonate and probably residual pore water. Now that ends up being a really special association because the presence of magnesium silicate co-precipitated with calcite microspar actually gives us extra constraints on the chemistry through which this microspar component might have precipitated. And so this feature here is, of course, of interest, but before I walk through what those constraints are, I'm just going to say a few words about microspar itself, its various petrographic expressions, and its importance within carbonate successions. So In most cases, calcite microspar is a thin sedimentary component. That is, it ends up filling primary pore space, as you can see in the images on the right-hand, ranging from intergranular cements, pore-filling cements, gets reworked into various formations as intraclasts. It has a unique petrographic expression in that it's comprised entirely of euhedral calcite crystals that range from about 5 to 20 microns or so in size. And all of those crystals share identical characteristics under cathodoluminescence, and they together represent what a few authors have drawn attention to as a unique crystal size distribution, which I'll discuss in later slides. Geochemically, microspar has always been a bit of a puzzle because it's associated with relatively high concentrations of strontium, but there's been little direct petrographic evidence for an aragonite precursor. In fact, if anything, it looks as though the precursor to this material was magnesium calcite. And so that sort of persisted as a puzzle in terms of figuring out the formation history of this component. On a broader level, this component really serves as a hallmark of late Proterozoic carbonates in the sense that in cases it can represent up to 90% of individual beds. Noel James and his group have drawn attention to this for years. It can comprise up to a quarter or perhaps even more of entire formations. Spectacular examples of late Proterozoic and early Neoproterozoic carbonate successions where that's indeed the case. Some microtextural data and geochemical data suggest that microspar is essentially a mud producer. So as it gets broken down and reworked into carbonate components, it can end up being the source of a lot of fine-grained carbonate through which lime mudstones are built. And we've collected a lot of data from the successions that we've worked on that suggest that this is the case. And so getting to the roots of how this component were formed in early Neoproterozoic seawater could give us important information about calcium carbonate chemistry in general. And the last point I'll stress here is that geochemical studies, so in particular carbon isotope studies, strontium isotope studies, suggest that microspar reflects coeval seawater more than diagenetic fluids. Sedimentologically, it's certainly the case that calcite microspar is thin sedimentary and forms while the sediments were barely lithofied. So there's presumably a lot of exchange of seawater and pore water during its formation. Don Sumner has brought up the point that by mass balance, you need a huge amount of seawater just to fill those pores with calcium carbonate in the first place. I think the same reasoning is true for almost any early calcite cement. So the magnesium silicates are important because it gives us a couple of extra constraints in the calcium carbonate system, and I'll walk through the logic behind this in the following slide. In case you're not familiar, equilibrium carbonate chemistry can really be described with 6 parameters, but because of redundancies associated with equilibrium chemistry, if we know any 2 of those 6, we can solve for the remaining 4. And those 6 parameters include pH, total alkalinity, which is essentially a charge balance parameter, though you could think of it as the concentration of titratable acids. The concentration of CO2, bicarbonate, the carbonate ion, and then the sum of those components, which is referred to as DIC, or dissolved inorganic carbon. Now, from what we know about magnesium silicate nucleation from experimental studies that we've done is that for kinetic and thermodynamic reasons, there is a minimum pH that's associated with nucleating this material. And as far as we could tell, that pH is around 8.5 or so. And that's actually quite an important constraint in finding this material associated with microspar, as we have in the Callison Lake Formation, as well as the Svanberg Fjellet. But what's also important, and another constraint arises from the requirement that the total alkalinity of that water that's producing magnesium silicate and calcium carbonate microspar has to be greater than 2 times the calcium concentration. And that's because in order to precipitate a lot of calcium carbonate and keep pH high enough to stabilize the magnesium silicate, we need residual alkalinity. So the precipitation of calcium carbonate withdraws alkalinity from the system in a 2-to-1 ratio. And so that's where this constraint really comes from. So we can get another way into the carbonate system through this requirement. But then that means that if we have any constraints on calcium concentration at all, we can solve for the entire system, because then we'll be able to constrain total alkalinity, and then that, along with the pH constraint, would allow us to constrain the equilibrium carbonate chemistry. And in a paper that Justin and I wrote in 2020, we went through this thought exercise and said, well, there are some fluid inclusion constraints from the Brown Formation that's dated to about 830 million years old, as well as gypsum before halite evaporites that are deposited through the Tonian, and all of those things together place constraints on calcium concentrations. So using the fluid inclusion data, let's say that the fluid inclusion data give us a range of about 9 to 12 millimole. If we say 9 millimole for calcium and then constrain magnesium and sulfate accordingly, we can work through the dissolved carbonate system and figure out where we are in terms of saturation state and other key parameters. So here's a plot that does just that. So this is the total alkalinity on the y-axis as a function of calcium concentration on the x. I've got modern seawater plotted as a blue box here. You can see the range of the fluid inclusion data that are, I should mention, somewhat older than the Svanberg-Fjellett Formation by about 15 to 20 million years or so. But you can see the 2-to-1 relationship between alkalinity and calcium here. So alkalinity levels are actually quite high if we specify a pH of 8.5. Now we can do this and work through the rest of the carbonate system, because we have 2 parameters. So we could solve for atmospheric PCO2, DIC concentrations, and then of course the saturation state with respect to calcite, or omega. Omega is defined here in the red as the product of calcium concentration times the carbonate ion concentration over the apparent solubility constant. And you can see one of the results from this exercise is that the saturation state with respect to calcite is unthinkably high going through this exercise. So we're looking at ranges of about 65 and higher. And so when we undertook this exercise, at first we didn't believe this result. And then we asked, well, wait a minute, what do we know about calcium carbonate nucleation in late Proterozoic seawater? And could saturation states of this type be sustained for any interval at all? And what really is this telling us about the formation conditions required for things like microspire and other distinctive components in late Proterozoic carbonates? So after that work, we kind of backed up and started to ask some broader questions. And so, as I mentioned before, in the absence of skeletal biota, how did calcium carbonate nucleate from Neoproterozoic seawater at all? What is it that microspire is really telling us here? And are these the geochemical relationships really valid? And then how could calcium carbonate supersaturation have been maintained on the million-year timescale, as is suggested by carbonate stratigraphy? So if it's really true you need this type of calcium carbonate saturation, how would that work? Excuse me. So our hypothesis, really modeled after John Grotzinger and Don Sunder's work in the 90s, is that kinetics probably played an important role, at least in reconciling some of these observations. Any geochemist knows that calcium carbonate precipitation is governed almost exclusively by kinetic factors, and there could be inhibitors in the form of common seawater ions that could be strongly controlling the dynamics of calcium carbonate precipitation. So we thought to investigate this process in a laboratory study that was really focused on understanding how calcium carbonate could nucleate from late Proterozoic seawater. And that's where my student Sasha Rostelis really dove and undertook some fantastic experiments to put some observational constraints behind this process. So we employed 2 techniques to investigate calcium carbonate nucleation from seawater. And those techniques differ because the first one approaches the point of nucleation from undersaturation, and the second approach approaches it from oversaturation. And this is important in order to ensure reproducibility and really obtain some important kinetic information. But the first experimental approach is through CO2 degassing. So basically what we did is we synthesized what we thought was representative of Tonian seawater informed by fluid inclusion constraints. We set a desired steady state partial pressure of CO2 to acidify the solution and make sure we're far below calcium carbonate nucleation. We adjusted the solution to a desired total alkalinity, and then we started purging the CO2. And because DIC is lost, but alkalinity is constant, the pH increases until you approach the point of calcium carbonate nucleation. And this is actually an approach that John Morse employed decades ago, and we basically borrowed this trick from him, but it's a fantastic way to investigate nucleation repeatedly anyway. Another approach is using constant composition experiments. And so this is from supersaturation. And so here we've got the same system, but we're controlling calcium carbonate chemistry and the state of supersaturation by auto titration. So we can pick a supersaturation, use titrants to make sure everything is held constant during calcium carbonate nucleation. So total alkalinity, DIC, pH, and so forth, and monitor the process that way. That's important because it gives us important measurements like induction time, which allows us to unpack the kinetics of the nucleation process. And throughout Sasha's work, we investigated a variety of potential inhibitors of calcium carbonate nucleation, but I'll say right now that of the inhibitors that we work with, so ferrous iron, sulfate, magnesium, phosphate ended up being the strongest inhibitor in that it drastically modified the kinetics of calcium carbonate precipitation. And I'll walk you through some of the results that we found. So here's a plot of pH on the x-axis and dissolved inorganic carbon on the y-axis. We've got dashed lines that represent different saturation states with respect to carbonate in this space, and the numbers of omega calcite appear on the left and then over to the top. All of these experiments were conducted at a fixed magnesium-calcium ratio of about 5.6, which is pretty close to what it is in the modern ocean, and it's on the high end of the fluid inclusion constraints from the Spiridol paper. So here are the results from some experiments that Sasha ran with no phosphate in the system. So this seawater composition actually looks pretty close to modern seawater. And unsurprising precipitate that we get from these experiments is aragonite. And aragonite precipitates again and again at an omega calcite value of about 20 or so. And that's consistent quantitatively with results that came out of John Morse's group in the 1990s. So there's really nothing here in that regard. However, when we include phosphate in the system, we end up observing some very different behavior. So in experiments where we've had 50 micromole per kilogram phosphate in the solution, two things happen. One is that the identity of the calcium carbonate precipitate changes. So in this case, we no longer see aragonite as the initial calcium carbonate phase. And the second thing that happens is that the threshold nucleation increases substantially. So instead of an omega of about 20 or so, the minimum omega that we observe in these experiments for any calcium carbonate nucleation is about an omega of 60. The red points illustrate that the initial phases are monohydrocalcite, and there is a green point here that produced high magnesium calcite. We did these experiments at different magnesium-calcium ratios, and when we decrease magnesium-calcium only slightly, so this is still what we call an aragonite C, but this is towards the lower end of the fluid inclusion constraints. The curves shift corresponding to omega calcite values, and I'll show you experimental results with no phosphate. So again, we end up with consistent results from what John Morse and his coworkers published decades ago. When we have phosphate in the system, a greater proportion of the experiments result in high magnesium calcite precipitation. And again, the threshold for calcium carbonate nucleation is quite high. So we see no nucleation in these experiments below about 45 or so. There was some other data that Sasha collected toward the end of her PhD that we incorporated in this paper, but that's about as finely as we were able to parse the nucleation threshold. So what is it that's going on here? Well, we can understand this process by taking measurements of what's called the induction time. And the induction time is the time taken from the time that supersaturation is established to the point that nucleation is achieved. And the induction time is an important parameter in classical nucleation theory because it allows you to derive some kinetic constants, and it allows you to calculate the point at which you should see nucleation over a given time. And this is really just a test of that relationship of induction time on the y-axis as a function of saturation on the x-axis, but this is in a slightly different form. But what we're able to do with these measurements is then predict the nucleation time as a function of supersaturation of calcite. And these are our experimental data plots. And the blue curve is the prediction from classical nucleation theory, or CNT. And classical nucleation theory predicts then that we shouldn't see any, or we should keep seeing nucleation below omegas of 50 or so, or at least the threshold below see nothing. And it's not a problem of time scale. So it's not a problem of us just not waiting long enough for nucleation to happen. This is a fundamental mismatch between what theory predicts and what we're actually observing. So there is a clear threshold below which no nucleation occurs. And we should have seen these observations, but we didn't. And so this is telling us that nucleation is not occurring in a classical way. There's something else that's controlling the process. So these points just emphasize that these observations aren't described by classical nucleation theory, and there is a real threshold in this system when phosphate is around, below which nothing happens. So we started doing in situ Raman spectroscopy to really monitor the evolution of solid phases in these experiments. And so this is a plot of various vibrational modes in Raman spectroscopy that tell us that the initial solids that form in these experiments are actually amorphous calcium carbonate, and that under varying conditions, the amorphous calcium carbonate will recrystallize to other crystalline calcium carbonate phases. Excuse me. So in this experiment here, we started off with amorphous calcium carbonate towards the initial part of the experiment. And we can see that the amorphous calcium carbonate actually recrystallizes in the solution to calcite in a relatively short amount of time. So identifying that the initial phase is amorphous calcium carbonate clarified the process and allows us to understand what exactly is going on here. So the big question is, why then does phosphate shut off calcite and aragonite nucleation directly? Why are we then just getting amorphous... Sorry, why are we then getting amorphous calcium carbonate nucleation and not calcite and aragonite right off the bat? Our thinking on this really stems from nucleation theory. And so we could write an equation for the nucleation rate in terms of a couple of key parameters. So capital D, the diffusion coefficient of aqueous species in water, the diameter of nuclei that are forming. And then there's a term that's embedded in an exponential argument that involves a number of constants, but also this term right here, which is the free energy barrier to nucleation. Now note that that term is made negative, and so as that barrier gets higher, the nucleation rate gets lower and lower, but this is a strong exponential relationship. And so what we think is going on is that phosphate being present in the solution modifies this free energy barrier. And so this free energy barrier can be written in terms of a couple of key constants, really the molar volume and delta GR, which is the thermodynamic drive for nucleation. But critically, it depends on the surface energy of the nuclei. And if phosphate is around, from what we know of phosphate adsorption studies and calcium carbonate phases, the adsorption of phosphate strongly increases the surface energy, and that should lead to essentially a collapse of nucleation rates to effectively zero. And we think that's what's going on when phosphate is present in solution. And what that means is that the only possible route for calcium carbonate nucleation is through an amorphous precursor phase. And that really helps us reconcile a lot of our experimental results. So just to summarize all of this here, we can kind of represent this on a flow chart. So we start off with mid-Neoproterozoic seawater of some composition with which we have some constraints from fluid inclusions. And our observations suggest that if phosphate was above 6 to 12 micromole per kilogram, we end up going down a pathway where we nucleate amorphous calcium magnesium carbonate, because aragonite and calcite nucleation, at least direct nucleation, is completely shut off by the presence of phosphate. And then depending on the magnesium calcium ratio, that amorphous phase will recrystallize to monohydrocalcite or magnesium calcite. In terms of reconciling these observations with synth sedimentary calcite microspar, the route through magnesium calcite is probably the most appropriate one, because that actually results in calcite that has unusually high strontium, and it actually imparts a distinctive crystal size distribution that results from Ostwald ripening of the amorphous material into calcite. And those are features that we've recovered from calcite microspar. And this, I think, helps us reconcile some of the geochemistry and petrography with some of the experimental results we've collected so far. And just a couple of words about that. We have done a bunch of crystal size distribution measurements on microspar collected from late Proterozoic rocks. But as I said, the geochemical characteristics, the crystal size distribution, and in comparison with what we've observed experimentally, really makes for a nice match in terms of quantifying the process and the carbonate chemistry associated with microspar precipitation. So I guess an important outcome of this is that amorphous calcium carbonate solubility may have regulated marine chemistry, at least periodically, through the late Proterozoic. And if this pathway is required to form microspar and to result in some of the key features that we're familiar with, this has some pretty interesting implications for the calcium carbonate cycle in the late Proterozoic. And a number of authors have summarized the distribution of microspar, or at least microspar-bearing components, through the late Proterozoic. So this is a recent annual reviews paper where they tabulated the occurrences of molar tooth. And so molar tooth, of course, is a sedimentary feature within which microspar is typically precipitated. But of course, we know that microspar occurs beyond molar tooth and is an important carbonate forming component in its own right, as I mentioned a few slides ago. But what this suggests is that the long-term maintenance of supersaturation does require some inhibition of calcium carbonate precipitation. There needs to be an inhibitor present in order to go through this pathway in the first place. And if phosphate was the key inhibitor, that suggests that common seawater ions may have opened up these pathways, and that could essentially tap into a diverse realm of calcium carbonate precipitation processes and products. So now all of this is interesting, but of course it leads to the question, well, is there a phosphate around in these carbonates? If there was phosphate in late Neoproterozoic seawater, how much could there have been? And for the last few minutes of the talk here, I'm going to talk a little bit about some data we've collected that gives us some constraints on that. So we've looked at a number of Tonian carbonate successions and have looked in detail at where phosphate might be and whether those carbonates can actually tell us something about phosphate concentrations in shallow seas. I'm going to focus on some data that we collected from carbonate rocks in Svalbard through the academic Rebreen group, including the Svanberg Fjellett Formation, which I talked about at the beginning of the talk. And this work was done a few years ago in Nordistlandet, in this locality here. And so I'll show you one succession. So this is a succession that runs through the Gruzdiep Formation and the Svanberg Fjellett Formation. This general succession is dominated by thinly bedded to laminated lime mudstones that appear to represent a dominant subtidal depositional environment. The whole of the succession shallows upwards somewhat because it passes through a significant stromatolitic accumulation. But you can see here on the left-hand side that this succession is dominated by talc and microspar. So these two components really make up a significant proportion of the depositional components within this succession. You can see some of the photographs here. The microspar imparts this frosted glass appearance, and the talc components and talc nodules end up having this sort of black oil and water texture. In some cases, almost all of the rock is actually dominated by microspar. So we'll show some chemostratigraphic data. So here's the delta C13 through this succession. It actually records a portion of the Bitter Spring stage. You can see bulk rock magnesium-calcium ratio increases as we shallow upwards a little bit, and manganese-strontium ratios start to move a little bit as we get into slightly shallower water and an increased propensity for dolomitization. What we've done is we've looked at bulk phosphate contents just by micro drilling different components of the rocks, so really targeting microspar. And right off the bat, you can see that phosphate concentrations in this succession and many others are really high, on the order of thousands of ppm, at least compared to modern carbonate sediments. The next question is, where is this phosphate hosted? What is the mineral? Solid state NMR ends up being a fantastic technique to employ to answer this question. This is a technique that you can do on bulk powders, and so obviously the textural information is obliterated. But you can see here a plot of different samples focusing on 31 phosphorus. And really what solid state NMR does is it gives you information about the nuclear environment of a nucleus bound in a mineral lattice. And so that's sensitive to bonding parameters and bonding environment. And it helps you identify mineral hosts for different components, like we've done with phosphorus here. So this is telling us that the dominant mineral host is apatite, and we can even use 19-fluorine NMR to get some more information about the type of apatite. So we see a particular defect that the fluorine nucleus feels when there's carbonate present above a certain amount. We can see that the dominant host from combined phosphorus, fluorine, and hydrogen NMR is actually carbonate fluoroapatite. So the familiar version of apatite that we see forming in marine diagenetic environments today. So the last question was, where spatially is this phosphorus accumulated? So we know that it's bound as carbonate fluoroapatite, or CFA. And we ended up answering this question using SEM and probe work, but then also repeated trips out to the Sanford Synchrotron Radiation Light Source, or SSRL. We used two different beamlines to do X-ray microspectroscopy and imaging, and that allows us together to look at the distribution of lighter elements like phosphorus, silicon, and magnesium, and then also heavier elements like strontium, iron, manganese, and calcium to assess things like the degree of diagenesis. And so here are some data from samples from the Svanberg field formation. So the petrographic image in the upper left is a little intraclast conglomerate that's cemented by microspar. And you can see the corresponding silicon and phosphorus maps here. The silica reflects dominantly detrital chert particles that are worked into the carbonates, but you can see a number of phosphorus hotspots associated with this thin section. And zooming in on those hotspots and really finding those in SEM shocked us, because it turns out that those hotspots are comprised of carbonate fluoroapatite and talc co-precipitates that have been worked up as intraclasts that have accumulated in the carbonates. And you can see some of these images here, and I'll draw your attention in particular to panel B, where you can see this talc cement that has individual CFA crystals on the order of a micron in size embedded within it. And this suggests that the talc and the CFA precipitated together from the same water. And these intraclasts have been worked into the carbonates as components through much of the succession. So here's another example from that same succession, a stromatolite that we chopped up, and we'll look at a thin section derived from the upper portion of this stromatolite. So it's turned on its side, but you can see the silicon and phosphorus maps show a number of phosphorus hotspots here. And zooming in on this with the SEM, we can see that this stromatolite is littered with tiny particles of carbonate fluoroapatite, essentially nanoparticles. So the nanoparticles are everywhere. And they range from about maybe 75 to 200 nanometers in size, and can be larger than that more rarely. And it turns out that these nanoparticles are actually pervasive in the Tonian subtidal lime mudstones that we looked at. So we've seen a lot of this in the 15-mile group. So this is from the Tutunduk inliers, samples that Phoebe Cohen has worked on and kindly let us borrow for the use of this study. And then also in the Coal Creek inlier from the 15-mile group. So again, you can see tons of apatite nanoparticles that appear to be accumulating within this rock and show no obvious evidence for diagenetic remobilization. We have observed evidence for phosphate diagenesis, and it does not look like this. We observed most commonly in the Little Doll group within which we've been working. Okay, so all of this information on phosphorus actually places some pretty important constraints on phosphate concentrations of the waters that gave rise to these minerals. So first off, there's a lower limit that we can place on phosphate concentrations, and that's because in order for CFA nanoparticles to form and survive sedimentation, seawater has to be at least at saturation or supersaturated with respect to CFA. Otherwise, they'll dissolve and they won't make it into the sediment. So in a way, these CFA nanoparticles are witnesses. They suggest that seawater had some minimum phosphate concentration in order to keep those particles around. And we can determine what this might be because CFA solubility is a function of calcium, phosphate concentration, fluorine concentration, and of course, pH. And this diagram assumes modern fluorine concentrations. It doesn't actually change the outcome of the calculation all that much. Again, we have some constraints on calcium. And then along with pH, we can actually solve for CFA solubility under different carbonate ion concentrations. And I've got a few different curves here corresponding to different levels of saturation with respect to calcite. But the take-home message from this calculation is that a phosphate needed to have been within about 2 to 10 micromoles per kilogram or higher in order to keep those nanoparticles around and keep them from dissolving. And you can even do the calculation of how long it would take for those nanoparticles to completely dissolve if seawater were undersaturated with respect to CFA. And it turns out the smallest particles wouldn't last longer than about 1 to 2 years or so, which appears, it seems to us like quite a short time scale, given that there isn't a huge amount of evidence for pretty rapid and pervasive seafloor precipitation in some of these successions. However, perhaps even more interesting than that, there is also an upper limit that we can place on phosphate, because the pictures I showed you provide solid evidence for the co-precipitation of talc and calcium phosphate. And we know that calcium phosphate precipitation doesn't directly form apatite from seawater. That's because of the magnesium that happens to be in seawater. So because of the magnesium inhibition effect, instead of forming apatite right off the bat, you form something called OCP, or octocalcium phosphate. We can write the reaction for this. So octocalcium phosphate stability is dependent on calcium concentrations, phosphate, and pH. It turns out that we have constraints on 2 of those, and so we can solve for phosphate. And this, we think, represents an upper limit on phosphate, so probably the highest that phosphate could have been in these depositional settings. So this is a plot of OCP solubility at pH 8.5. Now remember, this constraint derives from the co-precipitation of talc and apatite. And there are 3 different constraints on calcium concentration that we've come up with. There's constraint A on all the way to the left-hand side of the axis, and those are constraints on calcium concentration from gypsum before halite evaporite. So I mentioned before that Justin and I ran some reaction path modeling to work out the minimum calcium concentration associated with those, and that gives us 1 constraint. A second constraint are the fluid inclusion constraints, which I've labeled here B. I mentioned that the fluid inclusions, the Brown Formation, are significantly older than the Svanberg Fjellett Formation. But there is a third constraint, constraint C, and that's because this entire system, forming sedimentary calcite microspar through ACC, and talc and OCP, presumably driven through high pH, actually gives us together enough constraints to completely solve for the carbonate system and solve for calcium concentration. That's because of the alkalinity greater than 2 times calcium constraint, the pH constraint, and then also the constraint that we need to be at amorphous calcium magnesium carbonate solubility. And believe it or not, all those constraints pin calcium down to about 18 millimole per kilogram, which gives us a nice range of maximum phosphate in this system. And that phosphate ranges from about 30 to say 95 micromole per kilogram, which is substantially higher, of course, than the modern shallow ocean. Okay, so just to wrap it up here, our work suggests that phosphate was enriched in a number of early Neoproterozoic carbonate successions. The ones we've been working on are listed there. Importantly, this evidence jives with evidence for calcium phosphate biomineralizing eukaryotes that Phoebe Cohen and coworkers have published on. And also, this is consistent with kinetic influences on calcium carbonate production. So if it's really true that phosphate was present in seawater, this helps us understand the precipitation mechanisms of calcium carbonate and why potentially there could be so much microspar associated with this stratigraphic interval. And just the last thing I want to mention are some of the broader implications of that. And so I mentioned in the abstract that this could have messed with the ocean atmosphere carbon cycle. And let's just think for a little bit about how that could have been the case. Here's just the schematic of the major inputs and outputs of DIC and alkalinity to the atmosphere ocean reservoir. And of course, marine calcium carbonate precipitation is our dominant sink. Now, models of the global carbon cycle typically parameterize calcium carbonate precipitation according to a rate law that is dependent on saturation with respect to calcite. And that exponent n is typically tuned to about 1.7, and that kind of represents the latitudinal dependence of calcium carbonate saturation in the modern ocean. Now, it's important to note that that's usually parameterized as a continuous function of omega. So in other words, if omega gets high, you know, the output dependence scales to that exponent of 1.7. But of course, our experimental results suggest a completely different dynamic mode for calcium carbonate precipitation. So for one, aside from the nucleation requirements, we also know that in the presence of phosphate, the rates of pre-existing calcium carbonate growth were probably much, much lower. So we know that they could decrease on the order of 2 to 3 orders of magnitude compared to phosphate-free seawater. And that's really work that stems from Al-Muchi's work in the 1980s. And so incorporating all of these experimental constraints into the cycle models suggest that carbonate chemistry was probably highly oscillatory, probably flipping up and down in order to satisfy these constraints. And so we would suggest that a more appropriate functional dependence of carbonate precipitation on saturation might be something like this, perhaps a discontinuous function where when you're below the saturation with respect to amorphous calcium carbonate, your calcium carbonate flux could be very, very small because of the inhibition, the growth rate inhibition on calcium carbonate. But then, of course, if you're above that threshold, your precipitation flux could be huge. That exponent is probably something close to 3. And Zeeby and Westbrook wrote a nice paper that sort of develops the theory behind this. I think our laboratory experiments are actually putting some quantitative constraints on how exactly this mode of precipitation could behave. So anyway, I'll leave it there and just kind of leave up some of the major conclusions. So theory, experiments, and the analytical data we've collected suggest that Tonian marine inorganic carbon reservoir might have been highly unstable, and that also goes for the saturation state with respect to calcite. We think that phosphate's important to this. It suppresses normal calcium carbonate precipitation, and that really leaves ACC, or amorphous calcium carbonate, as the ceiling on calcium carbonate precipitation. And that could be reflected by some of the distinctive fabrics we observe in Neoproterozoic carbonates. Early Neoproterozoic carbonates, we think, record evidence for elevated phosphate concentration in shallow seas. This makes sense given micropaleontological evidence that I talked about earlier. And finally, if our results are representative of global shallow water calcium carbonate production, kinetic controls on calcite production, might have severely impacted marine carbonate chemistry. Because remember, we don't think we have a significant pelagic calcium carbonate sink the way we do in the modern Earth system. And the implications for things like atmospheric CO2 and the partitioning of carbon burial are significant and interesting to think through. And so thanks very much for your time. I'm happy to answer any questions you might have.
Great, thanks very much, Nick. We're going to transition to a question and discussion. And so just to start, I already have 2 questions lined up, but if you have one you'd like to ask, you can either type it into the chat and I'll ask it for you, or you can raise your hand and I'll signal you to unmute yourself when it's your turn. So the first one, Nick, was sent directly to me, so you won't be able to read it. It was, and I don't remember, it was at 8:27. I don't remember which slide you were on. I didn't take mental note, but here it is. It says, what about carbonates? Sorry, from K Sender SAR1. What about carbonates which are released from hydrothermal vents, which form seep carbonates, as suggested by Svensson et al. 2003?
Yeah, so I think any model of the long-term carbon cycle, and including the calcium carbonate cycle, has to take into account the different modes that alkalinity could be removed associated with hydrothermal activity. I personally haven't dug into those constraints, but any observational constraints on that would of course be important to fold into the story here. But yeah, I mean, the question is, how important was that process in removing alkalinity, and what was the push and pull against the shallow water carbonate factory? Absolutely.
All right. The next question is from Paul Hoffman. How do you reconcile calcite microspar with Tonian marine fibrous dolomite precipitation?
Fibrous dolomite. Yeah. I will say that what we know about dolomite formation, or just carbonate precipitation kinetics in general, is that I think dolomite formation is made easier by higher alkalinity. And if our results are suggesting, intervals of high alkalinity, I think on the whole, that makes things like dolomite formation a lot easier. I can't really speak about it in any more detail than that, because this, involves a number of other kinetic factors. But I would say the evidence makes sense from that, that broad connection.
I think you're muted, Alex.
Sorry, there were dogs outside my window making a lot of yippee sounds. Okay, so one more in the chat, Masha Prokopenko. Have you tried nitrate as an inhibitor of precipitation?
No, we haven't. We haven't actually worked with nitrate at all. That's an interesting one. Yeah, we should look into this.
Okay, great. So Jingjun Liu has his hand up. Please go ahead and unmute yourself and ask your question.
I think that's a fantastic talk. I was pretty amazed by that. I have several questions, but I can yield to Paul and later for more discussions. So my first question is, you mentioned the phosphate PI was being absorbed to the surface of carbonate, but because we know that the iron concentration in the Neoproterozoic is probably also higher, could it be that you have a competition between the absorption of PI to the iron oxide hydroxide instead of carbonate?
Yeah, so just to be clear, we think the adsorption of phosphate is important onto nascent calcite and aragonite nuclei. So that we think is the important process in shutting off aragonite and calcite precipitation. By mass balance, you don't need a lot of phosphate to do that because the nuclei are so small and there's probably not many of them there. So it basically stifles the first portion of the nucleation process. But I take your point, though, that there have to be other sinks for phosphate in the Earth system. And I mean, we don't have any proximal evidence to suggest that iron was important in these particular carbonate successions. We don't see any signature of, say, ferrous iron in these carbonates at all. So no suggestion of, say, iron reduction. Under these alkalinities and carbonate saturation states, you would precipitate siderite like crazy, given what we know about the iron carbonate system, and that doesn't appear to have been the case. There is a little bit of iron there, but it's mainly bound up as detrital things like biotite and chlorite. We don't see a lot of sulfide as well. So yeah, I mean, those processes are definitely going to regulate the phosphate cycle. I mean, we can only see sort of indirect evidence that phosphate was there and apparently plentiful in these depositional settings.
Yeah, a quick follow-up on that is that yes, first I totally agree with what you just said, but what kind of frustrates me is based on the compiled phosphate records, we don't really see a change in the sedimentary phosphate content throughout Earth's history, pretty much from the Proterozoic to Phanerozoic. So that is probably not an additional thing to that. What I didn't see also is a record of the phosphate content in carbonate change over time, because one of the hypotheses people kind of raise up of why they are not seeing a big phosphate deposit until the end of the Neoproterozoic is that the phosphorus precipitation is kind of scattered and in small crystal and diameters, and therefore it's probably not being recorded in the records. But if that's the case, if it's true, you have much more phosphorus in the mid-Proterozoic, Neoproterozoic ocean, you should see an elevated concentration changes in the carbonates. I know you kind of showed in several of your slides indicate that aspect, but did you specifically measure the variations over time?
Yeah, I mean, we don't have enough data to really put together, a data set that would speak to secular changes in phosphate concentration in carbonates through time. I think that's an excellent idea and something we would like to see put together. Another question is, the rocks that we're looking at reflect a particular depositional environment. We can't say, given the evidence we have, that there was a lot of phosphate, say, also in deeper water environments. We would like to know that, and there are ways I think we can get at this, but we're only really speaking to carbonate depositional environments here. But yeah, really good points.
Yeah,
okay, let's hop back over to the chat for just a couple quick questions, then we'll swing back to Paul and Shuhai. One from Greg Ritalik. If Neoproterozoic marine phosphorus was higher than modern, was Archean even higher or lower?
Well, I can't speak to the intervening interval because we've looked at a pretty narrow stratigraphic distribution. We have, though, sort of waded into the phosphate debate on the early Earth. I mean, our group just published a paper based on measurements of vivianite solubility in seawater, and it turns out that that was a problem that was very data limited. Turns out vivianite is way more soluble in seawater than people had originally estimated. And so that suggests that vivianite at least might not have been a lid on phosphate concentrations in iron-containing environments. Also, Michaela Ingalls has published some really fantastic work on phosphate incorporation in Archean carbonates. Birger Rasmussen has published data on apatite nanoparticles and iron formation. All of these pieces of evidence suggest that Archean environments might have been associated with high phosphate, compared to the modern.
Okay. Next question from the chat is, if the microspar represents mud precipitated in the water column, sorry, this is from Brian Pratt. If the microspar represents mud precipitated in the water column, could there have been pelagic carbonate production beyond continental shelves and epieric seas?
I think that's a really good question. So if the critical threshold you need to get over to get this stuff to form is just amorphous calcium magnesium carbonate, then it will form wherever its solubility is surpassed, and its solubility is going to be a function of obviously carbonate chemistry, but then also temperature and pressure. And this is something we scratched our heads over a lot, right? I mean, you could see microspar being preserved in cracks, but then you could see it broken down as just a mud that accumulates as well. So where is it forming, and then also where is it being preserved? It seems like it's best preserved when it gets injected in sediments, but it could be forming in a broader array of different environments. What we'd like to do is understand the pressure dependence on ACC formation a little bit better. And then what you could do is potentially put together a model of how pressure and temperature, might change the spatial distribution of where you could get this stuff to form. Don Sumner also suggested, injection of fluids through wave activity into sediments. I think that's a really neat idea. But yeah, I mean, that's a great question, and one I don't really have quite a good handle on.
Okay, great. Paul, go right ahead.
Yeah, Nick, it's great. You do stuff that nobody else does. So congratulations for that. Nucleation kinetics refers to carbonate production in the water column, but in shallow water carbonate successions, there's carbonate everywhere. So when you have, all these pre-existing sites, it's hard to see that nucleation inhibition enters into the picture.
That's a really good point, Paul. And I will say this, there is a misconception that the presence of surfaces, any kind of surface, calcium carbonate surface, microbial surface, makes nucleation easier. In this particular case, when we have phosphate around and we're supersaturated with calcium carbonate, the presence of surfaces makes absolutely no difference to the nucleation kinetics. The reason why is that the formation of ACC is the lowest energy pathway, regardless of whether there are surfaces there. And we've done experiments in our lab where we've thrown surfaces in these reaction vessels, and there's no difference. The nucleation happens when it wants to happen, whether there's particle calcite floating in there or not. And that's a counterintuitive result, but something that kind of falls out of the energetics of calcium carbonate production. But I mean, that's a great question, one that we've been asked and one we've spent a lot of time thinking.
That's a really interesting answer, because I thought it was biofilms.
Right, yeah. Well, that makes a difference today. It probably makes a difference today, but you're in a slightly different kinetic regime, and that you're talking about the direct nucleation of calcite, and microbial surfaces do make that easier. But when you have phosphate in the picture, it all goes out the window.
Doesn't
Right.
matter. Right.
All right, thanks. Shuhai, please unmute yourself.
Yeah, hi, Nick. Great talk. Thank you very much. I was just wondering, what the ocean needs to do to maintain such high phosphate concentration for a long time. And specifically, I was wondering how you slow down nitrogen fixation, because nitrogen fixation might keep up with the phosphate availability and to keep it low. So there must be something, either the source or sink. What are your thoughts?
That's a great question, Shuhai. We've also given this some thought, and I'm not quite sure where, we've landed in a place where we've answered that question, at least to ourselves. I think some insight might, so I guess one thing we could say about these depositional environments is that they were, at least some of the time, associated with pretty high alkalinity and potentially high pH. And that does introduce some complications to the nitrogen cycle. If you look at modern environments like Mono Lake, for example, high pH makes more of your nitrogen pool exist as ammonia, and ammonia is toxic to a lot of microbial processes. It also makes you bleed nitrogen because ammonia is volatile at relatively high pH. And so one possibility is that if these settings are alkaline, that could potentially be bad news for the nitrogen cycle, and that you could be leaking nitrogen in a way that nitrogen fixers might not be able to do what they need to do to use up all that phosphate. This gets into a lot of really complicated interactions, but these are possible. These could be mechanisms that might help reconcile that.
Okay, great. Thanks, Nick.
Okay, Jin, round 2, go for it.
Right. Thanks, Nick. Another question I have. Sorry, your talk is amazing. I have a lot of questions. Another question concerning the fluid inclusion of Natalie Spear's paper with Dick Holland and others. Good. I was kind of, because I was doing fluid inclusion analysis with halogen for my own project, I kind of stretched my head of how can I make sense of this data, because what I noticed is that in any of the halite collected throughout Earth's history, you only collect a fraction of chlorine, maybe 10% or much less. Well, in the Spear et al. Paper, I think, well, they didn't pay much attention to that because they are tracking the relative changes of different ions. So whether you capture 10% or the 5% isn't a kind of concern for them. But the same analysis the same challenges, because I was kind of interested in halogen, that has direct concern for me. But similar analysis or similar concern can apply to them, because you have much higher calcium concentration in your halite than your surrounding seawater, whereas some other elements is going into the different directions. So there's some element is being enriched, some element is being depleted. So how can we really use this fluid inclusion data to really say, okay, the magnesium to carbon ratio is really much higher than today?
I think so. On the basis of their raw data, they were careful to say that the exact magnesium calcium ratio, is subject to scatter within their data, but they were confident in that it represented an aragonite sea. As I recall, their raw data exhibited a pretty broad distribution of chlorine concentrations and element concentrations, within which they pretty confidently back calculate some of the major ion chemistry. I guess, I have not done this work myself, so I'm not sort of familiar with some of the analytical pitfalls. All I know is that Tim Lowenstein was associated with that work, and he's really kind of led the field in fluid inclusion development and reconstruction of paleo seawater. So I certainly trust a lot of data that comes out of his group.
Okay. Yeah, I can check his work for sure. Another question, is kind of dial back a little bit to the experiment of the phosphate. Well, because you have a lot of calcium, magnesium also, did you also kind of see the precipitation of calcium phosphate and try magnesium phosphate in your solutions?
So magnesium phosphate is really difficult to form. You need huge amounts of phosphate to get that stuff to form. There is a ceiling on phosphate concentrations that we observed in our system. There's something like 100 micromole phosphate. You can't get any more than that, and you start forming amorphous calcium phosphate, which then recrystallizes to OCP.
Thank you.
All right, Andre, you're up.
Yeah, great talk, Nick. I have a few questions, but if somebody sort of come in the middle, I can ask later. First one, sort of, how do you see phosphorus cycle in terms of mass balance? So you have some phosphorus concentration on carbonates, but probably it's not a huge sink. At least modern carbonate platforms are not huge sink. So not much of ion formations in Tonian as a sink, and shales, if anything, they show like low concentrations of phosphorus. So like, did you think like how you can reconcile a high phosphorus content in seawater and sort of where it goes? I guess you can argue that maybe a large amount of shales was buried at that time, but even if they have low phosphorus content, it still was significant sink. But anyway, I would be interested in your thoughts.
Yeah, that's a good question. You know, there have been a few compilations of phosphorus in shales through time. And I think, you know, I think the methods of the statistical analysis have differed among those different compilations. And so I would like to see more of that work to really kind of understand some of the secular changes. But you're right. I mean, a major question is where is the phosphorus going? So yeah, the carbonates might not be an enormous sink. I suppose you've done some back of the envelope calculations. I suppose it could be, but let's assume it's not. The question is this stuff just getting into shales as like orthogenic phosphate? You know, how can we tell? That's one of the next big questions for us, is that, you know, how many people have looked really, really, really closely at, you know, Neoproterozoic shales? There's phosphate in there, sure, but how did it get there? Is there any way we can tell? I mean, all I'd say is you probably have a pretty big source term, right? In the late Proterozoic. I mean, Forrest Horton wrote about this, you know, that the LIPs that are in place associated with rodinia breakup and volcanism, you know, could give you a bang for your buck in terms of phosphate. So at this time, there could be a lot of phosphate entering seawater. I guess that, you know, this doesn't really answer your question of where is it all going if it's not increasing in the shales. That's a good question. We don't have enough data to really put that question to rest.
Yeah, Simon Colton kind of working on it, and I shouldn't talk on his behalf, but I mean, he has different views from compilations by Noah and Chris, but the conclusions, I think, somewhat similar.
Mm-hmm.
But I guess it will come. So another question, so if your model is correct, you would expect that talc would be abundant in carbonate succession, not just Latonian age, but probably through Proterozoic and Archean. And I don't know if you have any compilation or evidence how widespread it is. And it leads to,
yeah. So two things. The talc requires a minimum pH, but the carbonate saturation speaks to, you know, high omega, and that can be achieved through alkalinity. And pH and alkalinity are two different things. I think talc is a special manifestation of high pH conditions, but you can form, you know, and with the experiments we've done and the numbers we've collected in the chemistry, you can form plenty of microspar without making talc. You can form this stuff at pHs lower than 8.5. So I think talc is kind of a, you know, special expression of, you know, maybe carbonate chemistry, creeping above a certain threshold, but it doesn't require that talc be formed everywhere. And in fact, it doesn't seem to be formed everywhere. It actually seems to be deposited only in special places as far as we can see. And I think that's telling us something important as well. And you know, presumably that gets harder and harder to do as you move back into the Proterozoic. If you believe that atmospheric PCO2 is higher, you know, your higher pH is harder to do, but you know, you can still have high alkalinity, I guess.
And I ask one more question and then let other people go. But for dolomitization, you know, it's people argued it for 100 years and still arguing. And it could be early dolomitization, like close to sediment water interface, but it could be later with fluids rich in magnesium moving from continents and maybe being hot enough and would have high silica content. So are you worried about that some of this talc could reflect this high magnesium and silica flux much later than sedimentation?
Yeah, I mean, I think the evidence that we've collected from these carbonates, especially in this Fannberg field, suggests that the talc is, you know, it's syn depositional. It is forming and then getting reworked into, you know, into carbonates as they're accumulating. So I think it would be hard to make that a later diagenetic phenomenon based on the textures that we've seen. And I guess I'm not really sure what you're getting at in terms of the magnesium required for dolomite and talc, only to say that I don't think there was any shortage of magnesium in seawater. You know, this is kind of a classic starting point with dolomitization, right? You know, dolomite, to make dolomite, you need seawater because that's where you get your magnesium, and there's plenty of magnesium left over to form talc as well, I guess. I think it's hard to really turn that knob hugely to make different outcomes.
Okay, maybe I let other people go, and at the end I'll ask more.
Okay, Greg has his hand up. Please unmute yourself.
Yeah, that was great. Thanks, Nick. I really enjoyed that. Very, very thought-provoking. Since the question of the sources of phosphorus was raised, I do have a paper in press. It's for GSA Today, and you can find it on their website. It won't actually be printed and distributed to members of GSA until December. But I showed a very big increase in the rate of apatite weathering in paleosols in the Neoproterozoic, but not a big increase in the weathering of ordinary bases like calcium, magnesium, sodium, and potassium, which increased greatly at the Archean Paleoproterozoic boundary. So the inputs, I think, are starting to become understood from, this is basically just messing with chemistry of paleosols. But in looking at your thin sections and your early diagenetic origin, I was really struck how much they look like nodules that you find today in estuarine soils, in intertidal soils, where you get a lot of vivianite and a lot of these really weird exotic minerals, where you get a soil that basically has, well, a marine foot and a kind of a non-marine meteoritic top. This is where you can have really pretty interesting chemistry, and of course biology in modern environments by fungi in particular. I'm wondering if you've thought about that aspect of the problem.
Yeah, the role of biology. Yeah, so we have thought about the role of biology quite a bit. So as I mentioned, in the successions we've looked at, there is not a strong indication that the phosphorus has been derived from diagenesis of organic matter. The reason is that it's hard to source all this phosphorus from anaerobic metabolisms, so say iron reduction and sulfate reduction, because there isn't really a whiff of iron in those sediments, and there isn't nearly enough sulfide. I suppose you could do it with aerobic respiration, but the problem with that is that it forces your carbonate chemistry in the wrong direction. And so if you want to source all your phosphorus from organic matter, you basically, you put a huge dent in carbonate, calcium carbonate supersaturation to the point where you can't get to where you need to be in order to keep your carbonate supersaturation high. So there's little evidence to suggest that you could get all this phosphate from organic matter, and also the carbonates are really organic matter lean, I suppose, and that kind of supports that. But I take your point that the soil successions you've looked at display some pretty interesting interactions with phosphorus. I mean, I don't know if this is what you're suggesting, but it's difficult to make these successions non-marine in this case, just because of the paleontology, the sedimentology, stratigraphy, and so on. But yeah, I mean, as far as we can tell, it just doesn't appear that the phosphorus is coming from organic matter. It appears to be delivered from the ambient water, the same way that the magnesium and silica for the talc, and the same way that the calcium and the carbonate are.
Well, I'm not saying that they're non-marine. I'm saying that they are the Neoproterozoic equivalents of mangrove soils. They're marine. They're sort of in between. It's kind of like Tony Brave was telling us a couple of weeks ago in a really great talk, that you're talking about very special environments that see both a bit of marine and a bit of non-marine. And
right.
Yeah. You can really do some complicated stuff in a situation like that if you can look at modern analogs for mineralization in mangrove swamps, for example.
Yeah, that's right. No, it's a good point.
But yeah, very stimulating. Thanks for that.
Thanks.
Cool. We have one more in the chat here. Does the oscillatory nature of carbonate precipitation suggested by your model help to explain the prevalence of mixed carbonate siliciclastic depositional systems in the Neoproterozoic compared to Phanerozoic? Or is there a mismatch in time scale in terms of inhibition being turned on or off? That's from Lyle Nelson.
Huh. Oh, that's a really good question. We haven't actually thought about that. I mean, so we just started putting together, a long-term carbon cycle model that takes into account our experimental constraints on carbonate chemistry. But that's a great point. It could be that an outcome of that is that you could, as you say, you could potentially explain some of the sort of flipping back and forth between carbonate and siliciclastic deposition if you're coming up with a specific climate response and a specific carbonate saturation state. No, that's really cool. It's something we'd like to think more about. Thanks for bringing that up.
All right, we have Jingjin put in the chat just saying the phosphorus concentration in the sediment water interface where phosphorus minerals precipitated should always be higher than the dissolved inorganic phosphorus in the surface seawater.
So could you just sort of outline the thinking behind that? Because we just discussed some of the evidence that kind of makes it difficult to get the phosphorus from organic matter, which presumably is a big reason for making that statement. But I'd just like to sort of understand that comment a bit better.
Yeah, I'm just thinking about say in the modern phosphorus profile, because of the biological scavenging effect, your dissolved inorganic phosphorus in the surface ocean is minimum, whereas the phosphorus being scavenging will eventually deliver to the marines, to the seafloor, whereas we observe that the phosphorus in the seafloor and in the water and in this this interface from the water column to the sediment is several factors higher than the dissolved one, which makes sense because even in the throughout Earth's history, when you have a phosphorus rock being spotted, it usually the weight percent vary. Well, it can reach up to 10 weight percent, I think. But pick any number, say 0.1%. That is like 0.1% is way higher than the dissolved total P in the ocean. So there has to be like a concentration mechanism making the P surrounding and that making the precipitation possible.
Yeah, definitely. I agree with that. It's just that the problem is we don't see evidence for obvious shuttles, of phosphorus into the sediment. But I definitely take your point, and those shuttles have to be important, in the broader system. But proximately, we just can't put our finger on what they are, and they don't seem to have been particularly important in these depositional settings anyway.
Well, carbonate platforms are very productive, so probably you have a lot of productivity, but remineralization of organic matter that would return phosphorus back to sediment water interface.
Yeah, I suppose so. I guess you just have to be careful with how much diagenesis you impose here, otherwise you can't get the carbonate chemistry to work.
Yeah, the next part, or the next comment in the chat does relate to this diagenetic impact. So from Chris Holmden, how do you know that phosphorus or phosphate isn't mostly syn-depositionally absorbed to sedimentary carbonate in shallow water settings and then diagenetically mobilized to form apatite during diagenesis?
Yeah. So, we have some evidence to suggest that that's not the dominant mode of apatite precipitation in the succession. For example, the talc apatite coprecipitates unequivocally show that both of those components were precipitated from a fluid, and that was, component was then floating around in seawater as well. And again, there's the constraint on the nanoparticles. You know, if you want to form the nanoparticles and have them accumulate in such a way as we see them, they have to be externally derived. It's extremely, there's no evidence to suggest that that's a diagenetic phenomenon. We know that phosphate diagenesis precipitates, phosphate along cracks and voids, but that's not where we see the nanoparticles. The nanoparticles accumulate along sedimentary beds and laminae, suggesting that they are an externally derived component that was floating around in seawater.
Okay, we have one more in the chat from Joanne, who says they're a biologist, and asking that is it possible to use carbonates to better understand phosphate and phosphonate concentrations in Neoproterozoic as well as phosphate?
That's a neat question. In theory, you should be able to see those signatures in the phosphorus NMR data that I showed. Because you're looking at the phosphorus nucleus, there's no requirement that it has to exist as phosphate or even as phosphorus 5. There's no reason it couldn't be reduced phosphorus. It'd have to look into the detection limits of those components, but NMR is a promising technique to be able to see if those components are recorded. I know Matt Pasek has observed evidence for phosphite associated with Archean carbonates, because I think he likes the idea that you can potentially get more reduced phosphorus from meteoritic inputs and so on. But yeah, that's pretty neat. I mean, I don't think anyone's tried, but it's not obvious to me why that wouldn't work.
Okay.
So Nick,
sorry, go ahead, Andre.
Yeah, just a couple short question. What I implied by fluids circulating, that hot or warm fluids would have higher magnesium and silica content, and this way they can kind of induce talc precipitation. And last question, you mentioned high strontium and magnesium calcite. Can you tell us more about what strontium content you would expect in magnesium calcite and how it compared to aragonite?
Yeah, the strontium concentrations in microspar get up to several thousand ppm strontium, which is normally, with sort of classical carbonate petrography, normally a criterion for an aragonite precursor. And then, you can go and go through all these techniques to, etch your thin sections and kind of look for, ghosts and form evidence of aragonite. But there isn't a whiff of evidence that that's the case for microspar, which has always been a real puzzle. So yeah, I mean, when you form magnesium calcite as it recrystallizes from the amorphous calcium carbonate, because the amorphous calcium carbonate is less discriminatory for trace element uptake, it tends to just take up a lot, higher concentrations of the strontium, and then that gets imparted to the magnesium calcite that you form, which is kind of interesting.
And I guess magnesium calcite would break down to form microcrystals of dolomite, and the rest would be calcite. Low magnesium calcite, right?
Yeah.
Okay.
All right, Nick, that's kind of it for what we have, but we would usually open up to open discussion. It is past 9:30, so I completely understand if you'd rather just move along. Or rather just, we can cut it here. It's been a long time.
Yeah, thanks, Nick. It was great talk and good discussion.
Yeah, thanks again. Thanks for all the great questions.
Yeah.
It was really fun. Thanks.
All right, well, thanks everybody. We'll see you next week. Oh, sorry, Brian. Yep, Nick, thanks a bunch. This was really great. Take care.
Cool. Thanks again, guys.